All right, let's dive right into this explainer. Today, we're tearing down the walls and looking at the actual, literal plumbing of the Internet of Things. We all hear the buzzword IoT thrown around constantly, but how does a tiny smart sensor sitting in a massive, muddy agricultural field actually talk to a server thousands of miles away in just a fraction of a second? Well, we are going to trace that exact path, following the data from the very edge of the network straight into the cloud core.
Right off the bat, we got to completely shatter this massive illusion. The illusion that IoT runs on some magical universal standard. It doesn't, not even close. Instead, it's all about making strategic choices on a metaphorical staircase of engineering decisions. Every single environment demands something completely different from the network, so building a functional system is really an exercise in choosing your compromises wisely. So, to make sense of all this, we're going to literally walk up this architectural staircase step by step. Network topology, infrastructure, the wireless medium, the conversation, and finally, we'll put it all together with an end-to-end system synthesis.
Okay, step 1. Network topology.
Before we even think about sending data across the globe, we have to figure out the physical layout of these devices in the real world. Think about it. You've got all these messy, completely incompatible raw data streams coming from totally different sensors. You can't just shove that straight into the cloud. You absolutely need a gateway. It acts as this crucial abstraction layer, a funnel, really, that grabs all those clashing protocols, translates them locally, and spits them out in a neat, standardized format ready for the cloud platform.
And this brings us to our first huge architectural choice. You've got direct device-to-device communication, or DTD. This is great for zero central reliance and crazy low latency if you're doing something really simple, but if you want actual scale, you have to introduce a device-to-gateway model. It decouples the brain, the application logic, from the physical hardware. Honestly, it's the only way to successfully manage these messy, heterogeneous ecosystems where a basic smart thermostat needs to live on the exact same network as a complex security camera.
Moving on to step 2, infrastructure and scalability.
All right, so our gateway has gathered the local data. Now we need the massive digital highways to actually transport it. But we hit a major roadblock, 4.3 billion. I really want that number to sink in for a second. That was the absolute, hard physical limit of unique addresses under the old IPv4 standard. For laptops and early iPhones, sure, it seemed like plenty. But for the Internet of Things, where literally every single light bulb, smart tractor, and heart monitor needs its own distinct address, yeah, that jar is completely full. It's fundamentally incompatible with the massive scale we're building today.
So to build out our wired, Ethernet, and fiber backbones for the future, we have absolutely no choice but to shift to IPv6. This completely blows the lid off that old jar, unlocking effectively unlimited scale. And even better, it gives us dynamic addressing, meaning your sensors can actually move across physical network boundaries. Think of a connected delivery truck driving through different cities, and they won't drop off the map or lose their connection.
Which brings us to step 3, the wireless medium.
Now, we are hitting the literal airwaves, and our decisions aren't just about software anymore. We are completely bound by the strict, hard laws of physics. It boils down to this one brutal trade-off at the edge. If you want a wireless signal to blast across an entire city, you are going to drain a small battery in no time. But if you want a tiny battery to last for 10 years, you can't broadcast very far, right? You can maximize range, or you can minimize power, but you can almost never do both without drastically sacrificing something else.
When we actually chart out power consumption versus range, our specialized edge tools just pop right out. Up high, cellular, 4G, and 5G give you massive range, but they eat power for breakfast. Wi-Fi, high power, terrible range. But look down at that bottom section. That is where IoT completely thrives. You've got Zigbee for low-power, short-range mesh networks, and LPWAN for low-power, vast range coverage.
Looking at the hard metrics really shows you the compromise. Zigbee is fantastic for, say, a localized smart home. It forms a nice mesh topology over maybe 10 to 100 meters, getting you decent data speeds. But LPWAN, which stands for Low Power Wide Area Network, is a totally different beast. To get multi-year battery life over a massive 15-kilometer star topology, LPWAN has to strip its data throughput down to the absolute bare minimum. We're talking just a few kilobytes per second. Perfect for a remote soil sensor in the middle of a huge farm, but literally useless if you're trying to send video.
All right, step 4, the conversation.
So how do these devices actually talk to each other and to the cloud? What's the language? Well, first up is MQTT, or Message Queuing Telemetry Transport. Picture a publisher, like our smart tractor, sending temperature data to a central hub, which we call the MQTT broker. The broker then hands that data out to whoever is subscribed to it.
It's an asynchronous publish-subscribe model, and it is incredibly resilient for spotty, unreliable industrial networks, mostly because the sender doesn't even need to know if the receiver is online right now. It just drops the message at the broker and gets right back to work.
Then, in total contrast, we have CoAP, the Constrained Application Protocol. This is going to feel a lot more like the traditional web browsing you do on your phone every day. It uses a synchronous HTTP-style request and response model. A client sends a GET request for the temperature. The server answers back. Simple. But the real magic of CoAP is that it does all of this with just a fraction of the overhead of normal web traffic. It's engineered specifically for those highly resource-constrained edge environments where every byte matters.
Putting them side by side forces you into, you guessed it, another trade-off. Do you need the heavy, deliberate, guaranteed delivery of MQTT? It runs on TCP, meaning it makes absolutely sure every single packet arrives. Great for critical telemetry. Or, do you need the featherweight, stateless efficiency of CoAP? CoAP runs on UDP. It fires off data super fast with almost zero overhead, which is perfect for tiny sensors where dropping a random packet here or there just isn't the end of the world.
And finally, step 5, end-to-end system synthesis.
Okay, let's step back and look at the entire master plan we just built. Follow the data with me here. Way out at the edge, you have these highly constrained devices whispering to each other using CoAP and short-range Zigbee. That raw data hits our gateway in step 2, getting translated and standardized. From there, it gets blasted down a massive, scalable IPv6 wired Ethernet backbone, our step 3 infrastructure. And finally, boom, it lands in the cloud core, plugging straight into an MQTT broker to feed our databases and dashboards. It's just this beautiful continuous chain of highly specialized tools.
So, what's the big takeaway? A successful IoT network isn't about forcing a square peg into a round hole with one single standard. True interoperability is an orchestrated symphony. It's all these highly specialized, incredibly deliberate trade-offs working dynamically together to make the whole thing hum.
As we wrap up this explainer, I want to leave you with a thought. Tomorrow, when you walk through a smart city or heck, just adjust your smart thermostat, think about the devices surrounding you. Ask yourself, what invisible pathways, what unseen trade-offs in power, range, and protocol are quietly shaping your reality right in that exact moment? The blueprint is literally everywhere once you finally know how to read it. Thanks so much for joining me on this deep dive.